Yes.
Okay. So we were doing examples. We will solve one last example and then go to problems. The examples are very important because they consider several types of possible question you might have. Okay. So we were done with the first examples. We still have only one example. So let us do it together. We have a water at 60 Fahrenheit is to flow from reservoir A to reservoir B through a pipe of length 1,700 feet and roughness equals to 0.0005 feet at a rate of Q equals to 26 feet cube per second as shown in the figure. The system contains a sharp-edged entrance and four flanged 45 degrees elbows. Determine the pipe diameter needed. So here they gave us the figure. You have from the initial state to the final state. Okay. So we will apply the energy equation between these two levels from point 1 to point 2. Okay. So first we know the variation in elevation, so we will include it in the equation. And we don't have here, let's say, we don't have a pump, we don't have a turbine, so we should only account for losses. Okay. And here, since we have several fittings, so minor losses will not be negligible, and we should account for that. In general, if they don't tell you neglect minor losses, don't do it. Okay. So whenever you have, for example, an interest region or an exit region where you have a sharp edge, or when you have fittings like this here, so you have several elbows in your figure. Okay. So in this case, you should take into consideration not only major losses but also minor losses. Okay. So here these are the four. You have four flanged 45 degrees elbows. Okay, so we should do 4 times k of the 45-degree elbow. And we should take into consideration also that we have minor losses here at the entrance level. And here at the exit level, we have also minor loss. Okay, now how to get the coefficient of minor losses? Sometimes they give it for you directly in the given. If not, then you should go to your tables in the book. I will do a summary for you for chapter 8. I will put for you in a sheet what are the main figures you use, يعني the Moody charts, the tables, the figures used for fittings. Okay, and I will put the main relation also as a summary. So here, let us see together how to find them. We can go to tables and figures. So first, if we go, for example, to the table of accessories, you can see here that in your application you have 45 degrees flanged elbows. So we will take k, the loss coefficient will be equal to zero point 0.2. I will select this value for the elbows of 45 degrees. And now, here in this figure, I don't have anything about entrance and exit, so I need to look at somewhere else. Here, for example, they give you several scenarios of exits, okay? And for each scenario, they give you the corresponding value of k. In our case here, in the exit, we have, or this is the case for the, let us go to the figure. It is the case, I think, for the inlet. Yes. So here, as you can see at the inlet, what will happen is that you will go suddenly from a very big cross section to a very small one. Okay. So we are in the case of a reduction of cross section. Okay, at the entrance. So if I go to my figure, I can see that this corresponds. I have a here. I have a sharp reduction, and it is a sharp edge. Okay, so I will select option B because option B corresponds to my case. Okay, and for this configuration, they said that for this configuration of a sharp edge entrance, I have that KL is equal to zero point 0.5. Okay, so I will select that the loss coefficient for this part here is zero point 0.5. I still need the exit K. So I will look at another figure because for the exit, as you can see here, at the exit level, you change suddenly from a small section to a very large one. Okay, so it's the opposite case of the inlet. So here to find the coefficient loss, I should look at another figure representing my configuration. So let us go, for example, here we can see the corresponding figure. You have that the corresponding figure is here also you have a sharp edge at the exit. So this is your corresponding figure, okay, which represents your case. And if you read the value, the corresponding sharp edged value is 1, KL equals 2. So we have found the coefficients, the loss coefficients for the different sources of minor loss in our problem. Okay, and now we are ready to write the energy equation. Okay, so the energy equation from point 1 to point 2, as usual. Here, as we said, no turbine, no pump. If we have a pump, we add it from this side, and we add HP from here, and if plus, and if we have a turbine, we add it from the other side. Okay, because as we said previously, the pump will deliver energy to the system while the turbine will take energy from the system. But here, since we don't have any of these devices, so we will cancel out these two terms, and we should take into consideration losses. So for HL will include both minor and major losses. So for minor losses, it's summation of KL times V square over 2G. And for the major losses, it is computed as FL over D times V square over 2G. Okay, so now I am done for sum of K. I have here, for example, as we said previously, for each part you take the average velocity. But since here you have one diameter over the whole system, then you will have one average velocity. This is why you can take sum of K into factor plus FL over D times V square over 2G, since the average velocity is the same everywhere in my duct. Okay, now what I should compute now, I should find the different terms. Let us start by the pressure. You have points 1 and 2 exposed to the atmosphere, so it is the case of zero gauge pressure, so I will cancel P1 and P2. You have, since you have incompressible flow and constant, so the flow rate is constant, and since the cross-sectional area A is the same everywhere from here to here, then you can say also that V, if you want here, no need, even you don't need the velocities here, and the velocity here is equal to this one. But since you are applying between 1 and 2, so just you need the velocity at this level. And at this level, the velocity is nearly zero. Why? Because we have a very large reservoir. So the velocity at 1 and 2 is zero, and so it will be cancelled from the formulation. Now, the velocity inside this duct here is not zero, but is the same everywhere. So here in your duct, since you have the same cross-sectional area, the velocity will be the same everywhere. Then this is the average that you want to compute. Okay, so here V is to be found. Why we don't know it here? Because the diameter is not given. The question is to calculate the corresponding diameter needed. Okay, so here Q is given. Since Q is given, I can relate the velocity and the diameter through the relation of volumetric flow rate. So now I can move to the second relation, which is for the volumetric flow rate. Before moving, just for Z1 and Z2, you can just replace them. You have Z1 equal 44 and Z2 equals 0. So since Z2 equals 0, it will cancel out. I will replace Z1 by its value. So I still need only to compute sum of K, and we already have seen together how to find them. Now, for the friction factor F, okay, I also don't know it. Okay, so I have here in my equation of energy two unknowns, V and F. So the energy equation, if you want, will give you a relation between the velocity and the major loss friction coefficient. So now let us try to continue the problem. So first, since the flow rate is given, what you will try to do now is to relate the velocity to the diameter. So we will write that V is equal to Q over A. Then in this way, we will relate V to D. Since as you know, also D is unknown. Yani in the energy equation, V is unknown, F is unknown, and D is unknown. So three unknowns in the energy equation. Okay. So I need other equations to close my system. I start by using the flow rate, Q, which is V times A. Since Q is given, I can relate V to D. So from the volumetric flow rate, I find a relation between V and D. But still, I have until now 3 unknowns and only 2 equations. So now I will move to, I need to find, if you want, other equations. Now, what I can do is I can replace V by its value in this equation, because V is found function of D from equation 2. Okay, so if I replace V by its value in equation 1, what can I find? I can find a direct relation between F and D. Okay, so by replacing 2 in 1, I can get just the friction factor, only function of the diameter. Okay, so this will be my relation. Okay, but also it's not enough, because it's one equation but 2 unknowns. So now you know always that when you have a major loss application, always think about the Moody chart. The Moody chart can help you to solve for your equation. Okay, and in the Moody chart, what do you need? You need to know what is the Reynolds number. Okay, so here also the Reynolds number is unknown, its function, but its function can be written as a function of the diameter, since the Reynolds number is V rho Vd over mu, which is the dynamic viscosity, or Vd over the kinematic viscosity. And then, since V is already expressed function of diameter, then Reynolds can be computed function of D. So until now, we have F as function of D. We have Reynolds as function of D. And of course, you know from the Moody chart that the important parameter is what? The third parameter is epsilon over D. But also this parameter is function of D. So this is one of the most complex problems, because I don't know F, I don't know Reynolds, I don't know epsilon over D. Okay, the 3 are unknown. But as you know, whenever I have these all my variables unknowns, I should do assumptions. Okay, last time we learned how to make assumptions, and we said, for example, that is epsilon over D is given, then I take F corresponding to the flat curve. Is epsilon over D is not known, I can start by a certain typical value of F, for example 0.02, and by iteration I solve. Very good. But why here? Why here it's not simple to assume F? Because look, if you look at the relation between F and D, it's a fifth order relation. And in the previous problem we did, if you want, it was a fifth order relation, but without this term. So if you don't have this term here, which is proportional to D, then you can say that if I know F, I can calculate D simply. But here, since you have D to the power 5 and D to the power 1, this is a complex equation. Even your calculator, you need an advanced calculator to solve it. This is why, in general, when you have such type of relations, instead of assuming F, because it will be difficult from F to get D, we will assume D. Okay? So only in general, when the function F is difficult to compute, and if I know F, it's not easy to get D from mathematical solution. Okay, so this is why it's better here, instead of assuming F, to assume the diameter, because if I know the diameter, I can just plug in and find F, and plug in here and find Reynolds, and plug in epsilon over D and find it. So if I know D, I can easily calculate all other parameters. Now the issue is how to start the assumption. Of course, here you need to know, you need to have like a certain if you do some application, you will know nearly what is the range of diameters we use. Okay, so for example, we can start, let's say, for a system, for a ducting system, we can start by saying no, D equal to 2 feet is an acceptable value. Okay, of course, as I told you, whatever is your assumption, you will end up with always the same result. But if you start by a very far assumption, it might take you more iteration to reach the solution. Okay, so if you start by 10 feet instead of 2, maybe you will need 1 more or 2 more iteration. So that's it. But at the end, you will end up with the same result. So here I will assume a
Doctor,
typical value. So I will
طب
say, I
احنا
will, yes.
how do we know انه what's the best to assume؟ انه هون we said انه we don't assume F, let's assume D.
I told you why. In general, you assume f, okay? And a good value to start with f, if epsilon over d is given, then always you take f corresponding to the flat curve. If epsilon over d is not known, you start by f equals 0.02, because in general, values of f are around this value, okay? Now, in this problem, why I didn't choose this method? Because look, if I tell you f equals 0.02, calculate d. Can you calculate it simply? It's a very complex relation to the power 5. If you have a calculator that can solve it, even sometimes the calculator, you have the shift solve option. If it's work with d to the power 5, it's fine. Then put it, okay? But sometimes it will take a lot of time to compute the diameter. Anyway, if you have a calculator that can calculate for you a d, if you impose f, then go for it. It's better, okay? If not, you can simply say that instead of assuming f and having a complex calculation of d, I will assume d, because if I assume d, I can easily calculate f and Reynolds and epsilon over d. So in this case, I will choose to assume d because the equation of f function of d is complex, so I cannot get d easily. So in this case, I will choose to assume d, okay? And for reducting,
طيب دكتور,
yes?
how can we assume انه close دي؟ يعني يمكن مثلا انا اجي هو هون
Okay,
احط
Ma'ana, I
مثلا
am
بدي اديك.
look,
طيب
I know sometimes it might seem difficult, but what I will tell you is that in general, engineers, when they do such application, they know that they are working in, for example, in a system, let's say to drive water from one location to the other. They know in the range of diameters, and the range will not be very large, so they can easily start with a certain small assumption. Okay, and in practical cases, let's say in such system, let's say we use a d in average equal to 2, so they can start by d equal to 2 feet, and then by doing only some iterations, they end up with a good result. Even try, if you try to start with 10 feet, try it, you will get back within 1 or 2 iterations more to the same value of d. Okay, in general,
يعني
if
خلاص
it's
can we start دايما
very
هيك
far,
with
look, if it's very
two?
far from these values that we are learning together, we will tell you in the exam, for example, start by this value to help you, okay? But in
Okay.
case the values we will obtain are close to this one we learned about, and if I don't tell you anything, start, if you have such a problem, start by d equals to p. And if you have other problems we did before, okay, start with f equals 0.02 if epsilon over d is not given. And if the problem is, if the range is more complicated, then I will tell you start by assuming this number. So in this way, I will simplify for you the analysis. Okay?
يعني إذا it's not given we start with 2.
Is that it's not given, and we are in the case of fifth order relation between f and d, start by d equal to 2. But if like previous problems, f is d can be easily calculated when I have f. Yani in the previous problem, for example, you don't have the second term which complicated the solution. Then you can start by f equals 0.0. And if d is given and you have epsilon, then you know epsilon over d. You start by f corresponding to the flat curve. Okay, as we did last time. Okay.
Okay.
So here, once you do the assumption, as we did last time, it's about doing iteration. So now I assume d equal to what I do. Once I assume d, I replace it here. So I assume d0, let's say, okay? I assume d0 equal 2 feet. I replace in Reynolds, I get, so here I replace d by its value, I get Reynolds 0. Then I replace d in this equation, I get f0, okay? Now, how to make sure that my assumption is not very far from the reality? What I will do, since now I have f0 and Reynolds, I go to what? Now, knowing 2 parameters, I go to Moody chart. From Moody chart, what can I get? I get the third parameter, which is epsilon over d0. And here, to know epsilon, I should look at the material of my part. Okay, so here, for example, let us go to the given. they said that the roughness here, they gave directly the roughness. Here it's directly given. The roughness epsilon is 0.0005 feet. Okay, so you have it directly. In case it's not given, they will tell you what is the material type. So for example, cast iron or any other material, then you can go to table and find epsilon. Okay, so here since it's given, I directly replace, and from Moody chart I can get what then? I get epsilon over d0, and since epsilon is known, I get, if you want now, I will get a new value of d. Okay, حسميها إذا بدكم d1 لأنه it will give me a new value of d. So now what should I do? I will compare d1 with d0. Okay, so now what the strategy is, compare d1 and d0. Okay, so if they are close, and if the difference is less than 5%, you stop. Okay, so when you get a difference, in general, we can specify for you. It might be 10% or 5%. We will tell you, for example, stop for a value close at 10% or 5%. We'll specify it for you. Okay, so you compare d1 and d2. How you do it? You do d1. D1 and d0, I mean. Okay, so you do d1 minus d0 over d0. d1 minus d0 over d0. Okay, if you get a ratio smaller than 5%, you stop. If not, if it's higher than 5, so if it's smaller than 5%, stop. And this is and d, the value of d I got is the final one. So now d1 is my value. I replace into so I am done, because what was the question was the diameter. So I can stop here and say the diameter is equal to d1. Okay, if not, what I will do, I should do another iteration. So if not, I do another iteration, and I will in the same procedure. And I do new iteration. So
And
what
you
do
find
I
f
do?
من d1.
So I find now new f. I replace into f here. I get new f1, and I replace into Reynolds. I get new Reynolds 1. Then I go to Moody chart. I get epsilon over d2 from Moody.
Doctor,
Yes.
this time, how much should we put d1? How much should we approximate it?
No, d1 you don't approximate it now. D1 you got it from here, from Moody chart. Okay, so d1 is, you only do a first approximation, is the first assumption only. This is the only assumption you should do. After this, no assumptions. From Moody chart, you do your calculation. You replace d0 in these two equations, you get f0 and Reynolds 0. These two parameters, when you go to Moody chart, will give you what? Because look, you know that
d1.
Yes, it will give you d1. So you know the value of d1. Now you compare d1 to d0. If the difference is small, you stop. If not, you should repeat. So what you should do now, you take the new value of d, which is d1. You plug d1 in Reynolds number here. You get a new Reynolds. Okay, you get Reynolds now 1. And you plug f, you get now.
Okay.
Now, if they are closed, here you can directly know if it will work or not. If they are already closed, then you can expect D will be closed. If not, you should iterate more. Here, I will take F1 and D1 to Moody. Okay, Moody chart. So here always the final step is to go to Moody chart, because it will give you the unknown you want. Okay, so I go to Moody chart. From Moody chart, I read now the new value of epsilon over D, which will represent epsilon over d2. Okay, so I calculate d2 and I repeat. So I will repeat until reaching two final values of these that are very close to each other.
Okay.
Okay, if you want, please try to practice on this. Okay, because we did a lot of examples last time. Okay, try to do iteration on Moody chart. And at the end, you have the corresponding value. You should end up with d nearly So here you should not you should not do several iterations, because look, the assumption was closed. If you want to make sure, try to start by D10, and you will see that you will end up with the same value, which is nearly 1.63. Okay.
دكتور
Yes.
قبل ما نبلش problems فينا نعمل summary عن كل شيء please
Yes.
بس إنه summary عن main idea.
Okay. Okay. Whenever you have in your problem, okay, always, you should look at, first you should write the energy equation. In any problem involving flow in ducts and you have accessories, so always the first step, okay, write the energy equation. Okay. Now, depending on the problem, you will know how to continue, because sometimes you have only one unknown. If you have only one unknown, so خلاص, you write the energy equation, you get your unknown, and it's fine. If you have several unknowns, you should try to find other relations, okay, to relate your unknowns. What are these relations? So first, the most important one is the energy. I start with it. Okay. Then the second relation I use, so two, for example, if I have incompressible flow, okay, I will use that Q equals to
The flow rate.
VA. Okay. It depends on the scenario given. Sometimes they give you the velocity, they don't give you the diameter. Sometimes they give you, you have several possibilities. And here, the 4 problems we did together, each example has a different input. But at the end, the method for all is the same. So I write the energy equation. I try to relate V and D, okay, or V and the Q. So it depends what is the unknown in my problem, okay? Now, third, I write the expression of Reynolds. I write, because I need Reynolds in my Moody chart, okay? And always Reynolds is rho V D over mu, but depending on the problem, if V is unknown, I find Reynolds function of V. If D is unknown, I find Reynolds function of D, okay? So depending what is my unknown, I express Reynolds function of the unknowns I have, okay? And the first parameter that is important is epsilon over D. So in case the diameter is given, this would facilitate a lot, because epsilon over D will be known. In case not, as in this problem, I should do an assumption, okay? So to close your system here, to close the system of energy equation, volumetric flow rate equation, Reynolds equation, and epsilon over D, finally, you should go to your Moody chart, okay? Sometimes, if for Moody chart, you need at least 2 inputs, okay? You need at least 2 inputs. Now, if you have these 2 inputs, it's fine. No need to assume anything. I go to Moody chart, I put the 2 inputs, I get the third one, and I am done. In case you have, sometimes you might have 2 inputs unknown, or like in this problem, the 3 inputs are unknown, okay? So what should you do in this case? In this case, you should do assumption, okay? You assume one value, and if you know this value, replacing back in your equation, you get the other values, okay? So sometimes if D is unknown, I assume D, let's say, I get epsilon over D, I get Reynolds, and then knowing these 2 parameters, I can compute, let's say, F from the chart, example, okay? So it depends on what is the assumption I did, what is the 2 parameters I calculated, and what will be my output. Here in this problem, I assume D, okay? Because I assume D, then I will calculate, based on D, I will calculate my other parameters, okay, which are F and Reynolds, and then Moody chart will give me a new value of D. In case I assume F, for example, if I assume F, then what should I do? Then, assuming F, I calculate Reynolds, I calculate epsilon over D, and from Moody chart, I get a new F, and then I compare, okay? So if you assume F, then Moody will give you a new F. If you assume diameter, Moody's chart will give you a new value of diameter. And always you compare your assumption with the value you obtain. And you continue to iterate until you reach 2 values close to each other. Okay. So this is the summary of the method. In all problems, it is the same method. What will change, as I told you, is the unknowns. So depending on my unknowns, I decide which method to use. Now, let us practice with other examples.
يعني دكتور ما في غير تو methods، يعني احنا بنطلع على الاف اذا معنا الابسلون على الكونستنت،
Yeah.
او اذا ما معنا الابسلون دغري we assume f equal to 0.02 او we assume d، صح؟
صح 100%. هول هن
بس
كل
هول
البوسيبيليتيز. انا اعطيتكم كل البوسيبيليتيز بهول examples. Okay. So
Okay.
here you have all types you can face. Now, examples. Let us do some examples. Water at 20 degrees is to be pumped through the 2000 feet pipe from reservoir 1 to 2 at a rate of 3 feet cube per second as shown in the figure. If the pipe is cast iron of diameter 6 inch and the pump is 75% efficient, what horsepower pump is needed? For water, take that at 20 degrees we have rho equals to 1.94 slug per feet cube and mu equals to 2.09 times 10 to the power minus 5 slug per feet second. And neglect minor losses. Okay, so please pay attention. If they tell you neglect minor losses, you don't account for them. If they don't tell you neglect minor losses, you should always look at your figure and try to see if I have minor losses. So here, if they don't say the sentence, we have minor losses here, and we have minor losses here, and we can find them as we did in the previous problem. Okay, but here, since in the given they said neglect minor losses, we will only account for major losses. Now, what are the important information given? First, you have here a pump, so pay attention that we should add the head of the pump. Okay, we have the total length L of the piping system is given, so L is known. We have the volumetric flow rate Q, we know it. We have D, the diameter is given, so this will simplify a lot when the diameter is given. D is given, okay, and I know the flow rate, so I can get what? I can get the velocity. So it's very simple here. No, nearly. I know D, I know V, I know Q, so it's fine. Now, for cast iron, it will help me to get what? To get the roughness. The material, always the material in the given will give you epsilon, okay? It will give you epsilon. So now, what I will do, as we said, first step, always write the energy equation. I will write the energy equation from this point here to this one, okay? Because I know conditions at these two levels. So first I know that P1 is the surface one is exposed to atmosphere, so P1 equals 0 gauge, and since it's a large reservoir, V1 equals to 0. I can say the same thing for state 2, so P2 equals 0 and V2 equals 0. So this will simplify a lot the energy equation. Now for Z, I will take a reference here because this will simplify my calculation. So whatever is your reference, you will get same delta Z. So here's the best choice to get is here or above. Okay. So if I choose the lower level as the reference, then Z1 is 0 and Z2 is 120. Okay. So now I can write my equation. Let us write our energy equation. Since we have a pump, we should not forget to add head of the pump. So H of P plus in general, we have P1 over rho G, okay? So if you want, we will look at the equation and simplify it, it's easier. So here, and before going to the equation, as we said, since you have the material, cast iron, you go to the table of roughness. The table of roughness will give you, depending on the material of the pipe, what will be the roughness value. And they give you the roughness value in feet and in millimeters. So if you have a problem in SI units, you take 0.26. If you have a problem in English units, you take 0.00085 feet. Okay? So here, since we are working in, it's I think English system, so we will take 0.00085. Okay. Now let us write together the energy equation. Okay. So as we said, we have the P1 equal P2, V1 equal V2. So I will simplify. Since I didn't wrote it here in detail, I will do it. Okay. So you have HP, you have a plus P1 over rho G, you have plus Z1, okay, and plus half 0.5 V square over 2G, okay, and of course here it is V1, half
Over
V1
G
square over 2G, okay, and we should add what? Do we have anything else from this side?
Z2.
No, from the other side, Z2, okay,
Ah,
equals to, from the other side, what do we have? We
Same
have
thing. P1 وZ2
P2,
وV2.
P2 over rho G, P2 over rho G plus Z2 plus 0.5 V2 square over أنا حاطة over 2 هون يعني بلا 0.5 أوكي يعني أو بتحطوا 0.5 أو بتحطوا over 2G. خلينا نشيل 0.5 أوكي. And what should we add also? The losses. The losses always we add them from the second, from which side we add the losses? First side or second side? Who will tell me?
From the second
losses
side.
from the second side, because everything lose is from the other side. So if you have a turbine, you put plus HT here. If you have losses, you put them from this side, because the energy at state 1 will be divided into the losses plus the energy at stake. Okay, so this is my equation. Now I will start to simplify. I have that P1 is 0, V1 is 0, P2 is 0, and V2 is 0. And since I considered the reference at level 1, so Z1 is also 0. So I will end up with the following relation, that H of my pump, okay, is equal to Z2 plus my losses, okay? And since they said neglect minor losses, I will only account for major losses, and major losses are computed as following. So neglect, since we neglect the minor losses, okay, then we have that HL is equal to only F, which is the friction factor for major losses, times L over D times V square, where V is the average velocity in the duct, and here it is the same everywhere, okay, because we have constant cross-sectional area, V square over 2G. So that's it. I wrote my equation. Now, let us see.
there is less
yes.
than a minute.
Sorry. Oh, okay, yalla, we will open a new session. When it will end up, I will send you a new link. Okay. So here you have we found the relation between H pump and the parameter. Now you can calculate the velocity here. Why? Because the flow rate is given and the diameter is given. So V is not unknown. So you just do V equal Q over A. This will simplify a lot your analysis. Why? Because knowing Q and A, we get V, so we can replace V by its value. So V is known. Okay. Now in this equation, if you want, I know the velocity, so I know Reynolds. I know the diameter, so I know epsilon over D. So I have two inputs that are known in my problem, Reynolds and epsilon over D.